So yeah, the timetable for today's session is on the course page on GitHub. So we'll start with a sort of little welcome and introduction. That takes us up to about 9:40. Then I'll give the first lecture, if you like, me talking, and then there'll be a 40-minute practical session. So the practicals are a chance for you to try out some of the things that I'm talking about as we go through. I suspect that many of you will come from quite a wide range of different backgrounds, so some of you might zip through it very quickly. Others might find you don't have time to get through the whole practical. I've set aside a little bit of time at the end of the course where I will still be around for any questions or discussion you might have on any of these topics. Very happy to hear your opinions and your views on some of this stuff as well, and interested to hear how you might apply it in your work. So we can talk about that a little bit at the end of the session on day 2, if you like. So yeah, with the practical sessions, I'm very aware that some people will go quickly, others may not be able to get through the whole amount of time, but hopefully we found a balance in terms of the time set aside for you to work on stuff and the talks. During the practicals, I will be around, and my colleague Nathan is here as well to help with any questions that you have. So we can be helping you during the practicals as well. I won't really be doing a walkthrough of the practicals or anything like that, but if you've got any questions, you can put them into the chat or raise your virtual hand, and I can come and give you a hand. Okay, so I should have introduced myself. My name's Adam Carter. I'm a program manager at EPCC, where I've been since 2003 now. I'm also currently I've just taken over as Director of Teaching here at EPCC. My original background was physics, a computational physicist, and I've then started working with some computational statistical physics for my PhD. Then went on, did more and more computery stuff, and then in my time at EPCC, I've sort of worked on a broad range of projects, some of them commercially, some of them more commercial, some of them more academic. I have done a bit of high performance computing more recently. In the last decade, I've been moving into the area of data. I am very much a generalist rather than, I don't have my own research agenda in machine learning or neural networks or anything like that. But I've sort of got a broad range of knowledge on areas related to data science. So hopefully I'll be able to answer your general questions in that area today. I'm also the program director for the University of Edinburgh's online MSc in Data Science, Technology and Innovation. It's a really cool master's program delivered by, I think at last count, 9 different schools across the university. So a really good interdisciplinary master's program on data science and related technologies. So if that's an online program. So if that is something you think might be of interest to you or any of your colleagues or anyone you might know, you can have a little look, search for that online. All right, so we're about to make a start. Yeah, I'll share my screen and we can move to the first lecture. So has anyone, before I do that, has anyone got any questions about the general setup for today, or things that you want me to be aware of before we make a start? Yes, Stephanie, you can.
Yeah, so good. Sorry, yeah, I was just wondering, is your recommendation to use ARCHER2 or for the practicals, or can we use our own laptop?
Yeah, so I'm kind of expecting you to use ARCHER2. Things are written as if you were to use ARCHER2. You're welcome to use your own laptop if you prefer. If you are doing that, I recommend that you download the Anaconda Python distribution, because that will have most of the stuff that we need, so that the practicals and so on are written assuming that you will be on Archer. But for convenience sake, or if you don't have an account on Archer or something like that, you should be able to do basically every practical today on on your own laptop. Because one thing this course does not really do, it doesn't really get to the stage where we're doing data science at scale, doing massively parallel machine learning on the machine. We get as far as looking at a framework called PyTorch, which can work in parallel. It can use GPUs and so on, but that's not really what we'll cover today. So most of the practical stuff can be done on your laptop or on Archer. So it's written as if you'll be using Archer, but feel free to use your laptop if you prefer.
Thank you.
Okay. So I'm happy to take questions as we go along as well. If I feel that we are running out of time or running behind or anything, I might save them up till the end. But if you do have a question as we go along, I'm happy to take it as well. So let's get back to the start of the presentation, and I will share my screen. Okay. So this course is an introduction to data science and machine learning. We'll actually spend most of the time talking about things related to machine learning, but I wanted to start off with an introduction to the slightly wider topic of data science, so you can see how it all fits together. Most of this material is available under a CC BY license, with the exception of some of the images. So full details are in the slides if you want to know more. So we'll start off by talking about what is data science, because actually this term is used in slightly different ways by different people. So it's probably worth me explaining my interpretation of what I think it means. So these are some quotes. I think this is something that we've used here at the University of Edinburgh to describe data science in the past. Data science is the study of the computational principles, methods, and systems for extracting knowledge from data. Here is another definition that I've seen somewhere else. Data science is the application of the computational principles, methods, and systems in order to extract knowledge from data. So for some people, it's a field of study. It's a little bit more academic. It's a little bit more theoretical. But for a lot of people, data science is a very applied subject. So it's the application of these things, bringing a lot of things together in order to extract knowledge from data. Here's a couple of more definitions. Data science is the extraction of knowledge from large volumes of data that are structured or unstructured, which is a continuation of the field data mining and predictive analytics, also known as knowledge discovery and data mining. So you'll see this definition has various different terms in it. They've been used to different degrees at different points in history. The knowledge discovery in databases was probably one of the earlier terms that was used. Later on, data mining became a thing. More recently, probably you'll hear predictive analytics, and in the last couple of years, of course, AI. So they're all related to each other. This definition mentions large volumes of data. As we'll see, I don't think data science has to be big data science. It often is, but it doesn't have to be. But it does capture the fact that the data can be structured or unstructured. So you can have very different kinds of data that you're working with in data science. The last definition is a Wikipedia definition from when I first put together these slides. It does change over time, of course. But it says data science is an interdisciplinary field, so that's an important thing to capture, I think, the interdisciplinary nature of it. So I've just seen a message in the chat about an error message trying to get a key. Maybe one of my colleagues can help you with that in the background. Otherwise, once I've finished this lecture and we get onto the practical part, I'll be happy to help with questions. Thanks for letting me know about that. So the Wikipedia definition, data science is an interdisciplinary field about processes and systems. So again, this is both the processes side and the systems side. We've still got the thing about extracting knowledge or insights. So it's going from data to something that's more refined or more useful. And again, this one also mentions the previous field. So we'll talk a little bit more about the differences maybe between some of these definitions as we go through. So this is also one of the original sort of definitions of data science, if you like. This is from Drew Conway. He was the first one to express data science pictorially using one of these, using a Venn diagram. And in his way of looking at it, he has data science as being an intersection of disciplines. So it's here in the middle. It's an intersection of what he calls hacking skills, but I think we can now probably talk about that as using computers. Over here, we've got math and statistics knowledge, and at the bottom, substantive expertise or domain knowledge, as it's quite often referred to. The fact that data science being an applied field, often you really have to understand the question or the domain in order to do good data science. So Drew put machine learning here at the intersection of the computing and maths. He put traditional research at the intersection of the maths and statistics and substantive expertise. I mean, I think there's, particularly speaking to this audience, probably computing has become so much more mainstream to do in the use of in all different kinds of science and research now, that this is maybe slightly more questionable. But this is how Drew arranged it. He had a danger zone between the domain knowledge and the computing skills. So worth keeping an eye open that if you do, some parts of machine learning and data science are so accessible that it's very easy to dive in to try to solve a problem with data science tools and techniques when you don't really have enough statistical background, for example, to interpret the results. So you've got to be a little bit careful sometimes about how you draw conclusions from your results. In practice, there is a lot you can do with machine learning, particularly if you're testing the output of your models repeatedly, where you don't have to have such a strong statistical background that you have to do strong statistical inference on all of the results that you get out. So not always necessary to have maths and statistics in your background, but ideally, good data science really is at the intersection of all of these things. Data science will probably be able to dabble in all of these things, including probably, hopefully, some, if not having full domain knowledge, they'll have the skills to speak to and communicate with and interact with domain experts. More often, particularly in larger organizations now, it's more common to have data science teams where you want to make sure that you've got all of these bases covered and it's not necessarily one person who knows everything. But ideally, yes, data science really is at the intersection. And where does the term come from? So just a very brief kind of historical context. Possibly one of the first uses was from John Tukey in 1962 in his writing The Future of Data Analysis. He says, "For a long time, I thought I was a statistician, interested in inferences from the particular to the general. But as I have watched mathematical statistics evolve, I have cause to wonder and doubt. I've come to feel that my central interest is in data analysis. Data analysis and the parts of statistics which adhere to it must take on the characteristics of science rather than those of mathematics. Data analysis is intrinsically an empirical science. So he doesn't actually say data science in that quote, but it's really the first idea of, well, can this kind of analysis of data to be considered scientific in some way? He stresses the idea of empirical, of doing experiments, and that is very much true of a lot of data science. So data science, when done properly, probably does justify the term science in the title. That's arguable, maybe some of it, but it does certainly have characteristics of science. So the idea of doing things empirically, doing investigations, probably doing things iteratively and repeatedly, and doing good data science also has a lot in common with doing good science. So doing things that can be reproduced and things like that. It probably justifies the use of the word science in its title, even as long as it's done well. 1974, so Peter Nauer in Concise Survey of Computer Methods, he does actually use the term data science. He says he uses the term freely, which is probably true of myself as well. I mean, I really use it as a broad term, generally speaking. Unless I'm being quite specific about it, I normally use the term data science to also encompass aspects of data engineering and data management, as well as the analytical machine learning bits of data science. So you can see that yeah, I'm using it as a fairly broad term, and a lot of people do so as well. Here's another quote. I think this is also Peter Nauer. Data science is the science of dealing with data once they have been established, while the relation of the data to what they represent is delegated to other fields and sciences. So a lot of data science is about, well, what common techniques can we use to get knowledge from data, whether that's in a biological context or a commercial context, or understanding data of citizens used in the government context or something. Miraculously, and it's one of the things about machine learning and data science that makes it so exciting, is that many of the algorithms, many of the techniques that are used can be used across all of these different fields, with some slight adaptations, but generally speaking, it's the same algorithms that are used to classify images, same types of algorithms used to classify images or something, as it is to do maybe speech recognition or something like that. So on the face of things, quite different domains, but a lot of what data science is about is the fact that the techniques and some of the specific algorithms are very portable, if you like. So yes, question. Yeah, okay. So is data science new? People have been doing data science for a long time. I don't think we can really claim that it is completely new. But what is new is the fact that it's now important enough for people to be studying it as a field in their own right and doing it. There is now such a thing, as I'm sure you're aware, as a data scientist, as a job title. So it is important enough now that it does have a sort of role now that's different from how it has been in the past. I was talking about data science as an intersection of disciplines. I've got my own little breakdown on the next slide. This actually is a few years out of date now. It doesn't look as pretty anymore, so I'm going to keep the old image that I found when I first did a Google search for what is data science, and then clicked on the images tab. This is what it came up with. So many different Venn diagrams, but the idea of data science being an intersection of all of these things, bringing things in from different angles, was certainly the point that many people were obviously trying to get across when they were answering this question. So this is another attempt at trying to show the different things that are involved in data science and how they relate to each other. There's a lot to it. There's firstly the applied part that we've talked about before, and the fact that this can be applied in commercial contexts, in research, academic research, scientific research, in medicine, government and not-for-profits. All of these domains can apply data science. We've got machine learning and data mining, which is the topic of most of what we'll talk about in this course, is here. But there's some other aspects to data science as well. The storage, the movement, the ingestion, the cleaning, the munging is the word sometimes used, or data manipulation, although that makes it sound like a bad thing. But basically the preparation of data is these are really important skills, really important things to understand if you're going to be doing data science. So they're often important prerequisite doing any machine learning or data mining. Similarly, even once you get some stuff out of your machine learning algorithms, what are you going to do with it? Quite often it's useful to be able to visualize that, or to turn it into new data products that can be shared by others. Data products could be reports, they could also be other sets of data. Maybe if you're using a data warehouse or something, and you want the results of your data to be used in different parts of the organization, dashboards, or to run additional queries on, or something like that. That could also be the output. Discovery and reuse. I mentioned data science and open science. This is another aspect of data science that I think is quite important. The sharing of data, it sort of links into fair data and all of these things. If you're doing data science well, you probably want to think about how the results are going to be reused in the future, whether that's openly and globally, hopefully in a scientific context, or whether that's maybe in a more controlled environment commercially or something like that, or in an area of research where it requires a little bit more thought about how the data is shared. You still have to think about how it's going to be used in future, even if that's just by a small group of people. There are some specific techniques and technologies used to handle big data. So I'll talk a little bit about that as we go through. Machine learning algorithms on the whole work best when they have got lots of data. That's a bit of a generalization, but they really come into their own when you have big data, large amounts of data. But you can see that they will work even on smaller amounts of data as well. So it doesn't have to be big to be data science in my book. Underlying all of these things, of course, is programming and scripting. So a lot of data science these days is done using R and Python. Probably Python is the most commonly used language. It doesn't have to be that specific language. I'm sure many of you have backgrounds in many different programming languages. But probably if you're going to learn one new one to make use of a lot of the machine learning frameworks, for example, then Python is a good one to use. And that's the one that we'll use in the practicals in this course, incidentally. And underlying all of that, of course, as well as all the history of mathematics and statistics, the statistical methods, understanding things like probability distributions and things like that are key to understanding and interpreting some machine learning techniques. All the underlying computer science algorithms and data structures, and a lot of data science engineering. So particularly when data science is deployed at scale, once you start having data pipelines and things like that, you obviously care a lot more about the infrastructure, the hardware, the services, and all of the software that's involved. So for many people, data science is all of these things. There's things that include being able to do maths and stats and some computer science and some software engineering or hardware engineering, right through from the programming, applying machine learning, looking after your data, sharing your data, and then applying it. And importantly, throughout all of these steps, we have the idea of the legalities and ethics. As I'm sure you're aware, these are quite important to data science as a whole, machine learning and AI in particular. This is somebody's idea. This is an image created by Swami Chandrasekaran in 2013. I'm not expecting you to be able to read the small print on this slide here. What I do want you to sort of see is the amount of stuff that's involved in doing data science. So if you are getting into this area, there are a load of different topics that you can learn about. As I say, to be a data scientist these days, you probably don't need to be able to do all of these things. If you're trying to build a data science team, you might want to think about whether you have got all of these bases covered, because they're all important aspects of data science. It's worth having a little look at that if you're looking at some of the things that you might want to learn about data science. Some people have also talked about data science as the fourth paradigm. In the context of science research, the first three paradigms being theory and experiment and simulation, that I'm sure many of you are familiar with if you're using services like ARCHER2. So the idea with simulation is that you normally provide some kind of model, you put it into a computer, you let the computer do the maths, and it comes out with an answer that's easier for you to interpret as to what happens in the simulation. A data science approach sort of complements that. It's a little bit different. It often involves looking for patterns in data. And the main difference with simulation is normally when you're doing data-driven discovery or taking a data science approach, the idea is that you don't provide the model yourself. The computer or the algorithms find the model from the data. Now, often you still need to provide, as we'll see as we go through, some kind of parameterized, where you describe what kind of model you're looking for, and the machine finds the parameters, but you're doing a lot less than you would in the case of simulation, where you're actually plugging in the full model into the computer and letting it turn the handle to see what comes out. So it's a sort of data-focused approach, and then you use machine learning algorithms to build your model, and then use the model. Whereas simulation, it's a sort of expertly prepared model based on previous, the theory about what's actually going on physically in the system. Okay, so yeah, so this fourth paradigm really is probably just the application of data science to scientific research. There's other aspects to data science as well, and applied in many different contexts. And you'll also see all of these terms mentioned when it comes to data science. Data analysis and data analytics, they often overlapped as well. No one specific definition. Data analytics tends to be used when it's a little bit more predictive and forward-looking. Data analysis is maybe used a little bit more when you're trying to work out what happened. You're looking at your data and you're just trying to understand the context of what generated the data, for example. Artificial intelligence now is a big one. most of artificial intelligence these days is done with machine learning algorithms. There is more to AI than just machine learning, although recently they overlap to a great extent. But AI probably, or at least originally, it was more reserved before it became a bit more of a buzzword, reserved for the sort of data machine learning that was that powered something automatic. It actually led to decisions being made. So it was more of a kind of automated machine learning process to arrive at something that appeared to be an intelligent system, rather than maybe things that were done traditionally in data mining, which was a bit more iterative process with human intervention at different stages to interpret the results and to try to understand what they mean, without necessarily a goal of having some kind of automated system at the end of the day. Miraculously, it's the same kind of underlying machine learning algorithms used in these two approaches. And again, the boundaries are blurred, but AI is probably a little bit about more taking it to the point where it's used in something automatic. Data mining is maybe more of an iterative process with humans involved. Applied machine learning, predictive analytics. Some people separate out data analytics from ones that are specifically predictive. Big data is really just about the size of the data, and I'll more about the size in a moment. What makes it big? And then this ties in, of course, to business intelligence, which is using all of these things in the business context to actually make decisions and make predictions and to understand your business. So in summary for this bit, data science means different things to different people. It's normally a matter of emphasis, and really as long as you understand what's in the different things that are involved, and you're able to work out whether people are meaning just the analysis part, just the analytics part, or whether they're also including all the data engineering and data preparation and data management that goes on around it, then it doesn't really matter what the precise definition is. So important aspects to take away: extraction of knowledge or insight from data, the fact that it's interdisciplinary, it's an intersection of many different things, it's got applications in multiple fields, and the combination of skills is new, but most are drawn from well-established fields. So if you're a statistician, or if you're a software engineer, or if you are somebody who has already used databases in the past, then you're off to a good start, because you have some of the skills that are required to be a good data scientist. So in the interest of time, I am going to sort of plow on. There will be a little bit of time for questions at the end of the talk. But for just now, I'm going to now go on and give a few slides about big data. So these slides are based on a presentation that was originally created for an Edinburgh data science event called Demystifying Big Data. So they're a little bit light they're sort of not meant to be entirely serious, but you can kind of see the idea behind big data and how it relates to data science. So when people say big data, what do they mean? So just like data science and just like AI, big data is a bit of a buzzword, and it means different things to different people. Data is everywhere. We're all using it. And of course, it's the case that one person's big is another person's normal. So there isn't really a cutoff beyond a certain number of bytes, then it becomes big. What I'm going to do is try and pick out some of the useful things from the hype around big data and explain why, yes, it matters, and yes, it does have to be treated differently from small data. So many of the definitions of big data boil down to what were referred to as the 3 V's: volume, velocity, and variety. And a pretty good definition, I think, of big data is big data if it's too big in volume or velocity or variety to work in the ways we've been used to. And of course, that's not an ideal definition because it's moving goalposts, because what we've been used to varies over time. But it's the idea of something that you have to think about differently in order to make the most of it, or to manage to work with if it's large in scale. So the 3 V's of big data are what came first. And I'll say a bit about what each of these mean. But of course, as soon as somebody came up with 3 V's of big data, people wanted to add more V's. So the first one they came up with was value. And actually, this is quite a useful one. I think if we stop here after 4 V's of big data, it's probably quite a good one. Because the whole reason we deal with the issues of volume and velocity and variety of data is because we believe there is value in the data and we can derive insight from the data. So it's the other side of the coin, if you like. You've got to deal with the issue of volume, the issue of velocity, the issue of variety, but what we're trying to get is the value. And there is a lot of value in data, as I think has been seen recently in AI, but also in the past, that many companies are storing a large amount of data, and they wouldn't really go to the trouble of doing that, probably on the whole, if they didn't perceive that it had value. But then, of course, people came along and said, well, what about veracity? What about validity? What about visualization? What about visibility? They just kept adding new V's. So different people over time have added different aspects to big data. I'll talk about what these terms mean in a moment, but I think thinking of these 3 as the core, this is what we're trying to achieve, and these are other sort of related aspects, is probably a good way of putting it together. So starting with volume. Volume could be that it's too many bytes, or too many files, or too many records, and then it can be at sort of different levels as well, to fit in cache, or to fit in memory, or to fit on disk, or to store at one site. So again, at different stages and to different people, these kind of cutoff points become important. There are points at which you have to change the approaches, the algorithms that you're using to work with the data. The other aspect is velocity, and this is about data which is arriving too quickly. So whether that's coming from sensors that you have to read, whether it's coming from transaction data, whether it's coming from streams of data from the internet as a whole, whether it's coming from a big from particle accelerator sensors or something, and you've just got so much data that is arriving. Some of the traditional batch-based or traditional techniques of collecting all the data and then analyzing it don't work. So a lot of big data is about building pipelines and using other approaches that allow you to deal with data in flight or as it's arriving, so that it can be processed quickly. The other aspect, of course, is data that needs to be available very quickly. Again, if it's going to be used in real time to, I don't know, steer a self-driving car or something, the data needs to be available very quickly, or the answers from processing the data need to be available very quickly. Variety is the idea that big data is too unstructured to store maybe in a traditional database or to process with traditional tools. The data that we have to work with these days comes in many different types. It's not just tabular data that can be expressed in a nice CSV file. We have images, we have sensor data, we have video, we have sound, we have tweets, or whatever you call them these days. They have all of these things are different kinds of data that have to be dealt with. And again, the exciting thing about a lot of the machine learning algorithms is that once interpreted quickly, the same kind of algorithms that are used for classification of tabular data are also usable for image data as well. But we do at least, the techniques involved in data preparation or cleaning or visualizing for these different kinds of data is going to be different. And value, as I've already said, this is the reason that people are doing big data. The large amount of data that we have available means that we can genuinely do things that we couldn't do before we had all of this store of data. Veracity is about the idea that the more you use data that others have collected, which is a big aspect of what big data is about. Normally, a lot of big data is found data. It's data gathered together, maybe from transactions or from other people's research in the past that you're bringing together. And it's harder to be sure where it came from and whether it's actually correct. So there are aspects of big data that are involved in the amount that you trust your data. And there are approaches out there to help deal with that. The data might be correct, but again, is it actually suitable to answer your question? You could flip that on its head. Another data science kind of approach to the problem as well. Start with your data and see what questions it could answer. You can do that sometimes, but normally with data science, it's still very useful to have a clearly defined question that you're starting with to try to see if your data can answer it. So yes, do you have the right data to be able to answer your question? Is it complete enough? Are you sure that it relates to the right population, the right things that you're trying to draw conclusions about? Visualization. So at some point, humans have to consume the data in some way. As it becomes larger, how do we do this effectively? So there are branches of big data that focus on how to visualize data at scale. Visibility, when people talk about this, they're talking about how do we make sure the data is visible to everyone who's meant to see it. So in a scientific open context, this might be about sharing the data, making sure, or inside an organization where the data is meant to be visible to everyone, can it be understandable to everyone and available to everyone who's meant to see it, but also invisible to everyone who's not meant to see it or hidden from those people. And again, who decides who's meant to see it anyway? So this is where we start to get into things like regulation, legal aspects, ethical aspects, private data, sharing it. And there are huge areas of data management that relate to this aspect of looking after data. Yes, Stephanie.
I was just wondering, I mean, especially the visibility stuff, that is not solely related to big data, isn't it? I mean, even if it's small data.
That's true. You're right. That is an aspect that needs to be taken into account whatever kind of data science you're doing. I think when people talk about it in the context of the 3 V's or the 7 V's or whatever, I think it's like a lot of these things, the problem just becomes harder when we do it at scale. And some of the aspects of visibility, like data protection and so on, become harder when you're bringing data sets together, which is a common thing to do again for big data type applications when you're taking internet scale stuff, for example, and trying to combine it with maybe personal data about your customers that's within the organization. It's very easy for things to leak out, and that wouldn't have happened if you were working with a specific, well-defined data set that you had complete control over. So you're absolutely correct that visibility is something that really, or at least data security and data privacy are things that need to be considered whenever you're doing any kind of data science. But I think when people talk about it as being one of the V's, They're just expressing that it becomes even more challenging when you are using a lot of large found data. That's a good question, good point. Variability is really about the fact that all of the above that we've talked about so far can vary with time. One partial solution to this is cloud computing. A lot of big data is done in the cloud. One of the advantages of this is the sort of the elasticity of cloud resources. So in theory, at least, these scale as if you suddenly need to process a large amount of data, you can bring on other computers and to help solve your problem in a short space of time by scaling out quickly. But of course, cloud computing is not the solution to all of these things, as anyone who's involved in supercomputers and HPC, I think, would also be very aware. This is maybe a slightly older slide now, because I don't think people do make this assumption as much as they used to. People used to have this, if you've ever heard of Hadoop, this was one way of dealing with large amounts of data. But I don't think Hadoop is the solution to all kinds of big data, just like any of these single technologies, whether that's certain kinds of databases or Hadoop. Can it solve all the problems? No, it's just one solution to some of the problems of big data. Hadoop is, well, as well as doing things like the distributed file system that it provides, it's ultimately just an implementation of MapReduce, which is a reusable parallelization strategy applicable to large data sets. So in some contexts, particularly for sorting, filtering, counting type problems, it's very good for processing large amounts of data without explicitly doing the kind of writing the parallelization code, things like MPI, that you would have to do if you were trying to parallelize the problem yourself. What about NoSQL? Again, this is one solution to some of the problems. So these databases are designed to work with larger amounts of unstructured data, for data that wouldn't necessarily fit on a single disk. So in a lot of cases, SQL data, if you don't know what kind of database you need, I would still recommend that you start with a traditional relational database. But once you understand what the limitations are with your data, whether it's changing too frequently and you have to update the schema, or whether it is too big to fit in a single data center, if you're working globally and you're trying to keep things in sync or partial sync, or where you don't always need it to be in sync, but you need the data to be very accessible, there are reasons why different kinds of NoSQL databases can be very helpful. They're often just relational databases with certain constraints relaxed so that they can work more efficiently at scale. So in summary, big data then is about having to think differently about the data that you work with. It possibly means scaling out and not just scaling up. So scaling out means using many computers. It's a kind of cloud-like elastic approach. Rather than building one super fast computer to solve your problem, you might want to use a more distributed approach, which can be less efficient, but it can scale larger, and it can be, in some contexts, cheaper because you don't pay for what you don't use when you're not using it. It probably means using new tools, but it really can provide new insight and offer more value. So even beyond the hype, I do think that there is still a great future in making the most of well curated, well prepared, well thought about data to provide new insight and to drive machine learning models and things that we'll be talking about later in the course. Okay, so that brings me to the end of my kind of general introduction to data science and big data. We're now going to focus really on the machine learning parts from now on. But if anyone's got any questions, on data science and big data, I'm happy to take them. If not, then, or if one occurs to you later, I can take it later. But what I suggest that we do now is to move on to the first practical session. So hopefully you will all have seen the GitLab pages, and all of the practicals, the points that you need to see can be accessed through these links in the timetable. So this first practical, it's kind of twofold. To be honest, one of the things is it gives you an opportunity to see if you can connect to Archer and to set up to run what's called a Jupyter notebook. So this is a web-based interface that we use for some of the practicals on this course. So it's really about just sort of getting you going and getting you connected. Once you've done that, I've tried not to reproduce what's in the Archer documentation, because it's really the steps that you need to go through are described pretty well in the Archer documentation. So I'm asking you to follow, and if you've got any questions, come to myself or to one of my colleagues here. And once you've done that, to get you going, I was going to suggest that you try out some of the content from the data carpentry course. Some of you may have done this on a previous Archer course, but it's a good place for us to start here. It gives you sort of familiarity with Python, with the Jupyter notebooks, and lets you practice some of the data preparation that we had in the slide over here, the data cleaning, the data pre-processing that is so important as a prerequisite to doing good machine learning. So first practical, have a look at the documentation for opening a Jupyter notebook, have a shot at doing that. If you've got any questions, we'll try and answer them, and I'll be around until 11 o'clock, when I will also take a short break. So if you have any questions as you go through the practical, you can type them into chat, or if it's not too busy, you can open your microphones and chat with me directly. But you can now sort of move on to the practical and give it a shot. Okay, so you work T01 as the example. You will have your own workspace that matches the so it is. So maybe Juan, or Juan, if you're around, is T01 the space?
I think Juan's headed off. He's not at the moment.
Okay, thank you, Nathan. So is T01 your work account? It's definitely your. Okay, the way I can check that, if you just go to your home directory, type CD, and then type pwd, and it'll show you what your home directory is. If you're able to show me what that is. No problem, Gudrun. So Gudrun, we were asking you if you could let us know what your error message was. Tiramisu, if you're able to tell me what your home directory is by typing. Okay, so there you go, Tiramisu. You need, instead of typing work T01, you need to have work TA138, TA138. So in Gudrun's case, permission denied public key. So it's not even getting as far as asking for your key. Yeah, you've uploaded the correct key, the public version. Good. What could be the problem? Gudrun, are you able? Yeah. So, okay. So there's a few people asking about directories and accounts. So let me just show you in the Archer documentation. When we have a line like this one, work T01, T01 a user. So T01 T01 should be you will have TA138, TA138 instead. And then the a user, yes, is your username. So in your case, probably, yeah, the TA138AB looks correct, Aaron. So this is the bit where you have to substitute your own work directory on Archer. Yeah, so if your home directory is in home, you need to navigate to work TA138, TA138, your username to run jobs on the compute nodes. That is correct, yes. So Nathan, okay, Nathan, Gudrun, Nathan is going to contact you directly. So for anyone else who's following along, one of the first steps that you're going to try and do is install Jupyter Lab in your work directory. So this is the relevant part of the documentation that you need to try. So you will do a module load, create Python to start with. And you'll have a line like this, but it will be replaced with your own account. So in my case, it's work Z19, Z19, ARCHER2-Archer. So this will be different for you. So that's what I have. And make sure that's in my path. And then you should be able to install Jupyter Lab. I've already got it installed, so it'll probably go pretty quickly for me. Might take a little bit longer for you, but hopefully they are the steps that you need to go through to get the lab onto your machine. Yes.
Just to add, so I did it in a virtual environment, and I had to upgrade pip to find the correct Jupyter lab. So if anyone's doing it in virtual environments, run the command pip install -minute upgrade pip.
Thank you. That is useful advice. So environments are a nice way if you've got different. Yeah, I can zoom in a bit. If you've got different. If you're using different Python installations to do different things, you want different packages, and you're not quite sure how they interact with each other, environments are quite good for keeping things in separate pieces. So for anyone who does want to use the virtual environment approach here, you will uncomment that line as mentioned in this comment, and then you can remove the user flag here. So environment's quite nice for keeping things tidy, especially if you're doing different sets of packages at different times. There's documentation about the environments on the same page further up, so that if you are interested in learning about the environments, you can follow the instructions up here. So we've got a connection issue for some people. SSH public key is in local directory. So this is so for different people, this might look slightly different depending on whether you're on Windows, Mac, or Linux. But so Aaron, are you using Windows or Mac or Linux? It shouldn't matter, but you're using Windows, right? I don't think I've got my Windows laptop here. Are you using MOBA Xterm, or are you using PuTTY, or are you using SSH with PowerShell, or are you using SSH with Windows Subsystem for Linux? Which version of SSH are you using? SSH with PowerShell. Okay, so that should be fairly straightforward. That normally works quite well. So can you see the public key is in local directory? So one thing you can try is when you're issuing the SSH command to connect, you can put in the -v flag. So if I try to connect here, you can add in, I think it's just like that. Yeah, a -v, and it gives you a lot more information about what it's trying to do behind the scenes. It's a bit boggling, but it can sometimes help you debug. It'll tell you, for example, where it's looking for the keys. So in my case, it tries various different things until it eventually tries public key, and then it offers my public key, and the server accepts the key in my case, and then it's asking for the passphrase. So you could look at the bottom maybe and see what key it's trying to offer and see if it's in the right place. It's looking for the wrong key. So it's got a default place of where it looks for a key. So Yin-Hoon, you can actually try it from the login node or the compute node, I think, for today. We're not doing anything computationally intensive, so it's maybe easiest just to try it on the login node. If you are wanting to practice how you would do it for the compute node, so you could practice doing things that are a bit more computationally intensive later down the road, you could try that to make sure it works for you. But for what we're doing today, it's perfectly fine to use the login node. So Aaron and anyone else who's having issues with keys, this -I flag should, in theory, tell it the key to use. So this is a relative path from where I am at the moment. So I'm in my home directory. So it's using the private, and this is the name of the private key. So you don't have .pub on the end here. That should tell it explicitly which key to use when it's connecting, if it's working as it's meant to. So for those of you who've maybe been a bit luckier and who've got Jupyter installed and you're trying to load the notebook, I'll just show the next step just so you can see it working. I'm going to do this slightly simpler version of just running JupyterLab on the login node, so I'm going to go straight to step 3 as instructed here. Then I'm going to run the JupyterLab server. So this is in the connection that I already have, where I just installed JupyterLab. This first line here, the Jupyter runtime directory, I don't know if you'll necessarily need to use it. But let's follow the instructions and then start JupyterLab. So you should see something a bit like this when you start JupyterLab. Hopefully with lots of green and yellow here and no red on the left. A red is an error message. So if you're seeing red, something beginning with an E, then maybe there's an issue with how things have been installed. But otherwise, what you should see at the bottom here are some web addresses. And this is what you will need to use to connect. So that you've got your your Jupyter notebook server running now on Archer, what you need to do is connect to it. And you connect to it through a browser. And it's the way of doing that is to connect to a browser on your local machine. So you can use whatever browser you're familiar with, Chrome, Safari, Edge, whatever. So some people are getting, you're using pip version 2204, 2332 is available. For me, that wasn't a problem. I haven't upgraded my pip and it's just fine. I think one of our other participants was saying she'd set up a virtual environment, and for her, it was useful to upgrade pip with the command given there. For me, I didn't need to do that, but if you're having problems, you could try it. It's you. You've got connected, but you're having trouble with your passphrase. Okay. So using the one. Okay. So there's two things that you're going to be asked for. One is the passphrase that was given to you that you typed in when you created your key pair. That is what's called the passphrase. Okay, so when it asks for passphrase, that's the one that you created, that you typed in when you created your key pair. The OTP is a one-time password, and that's the one that you get probably from your phone or from any other web-based authentication apps as well, like Authy or things like that. But I'm using Microsoft Authenticator, which works well for me. So I get a 6-digit number from Microsoft Authenticator on my phone, and that is the one that is typed in when you when it asks you for an OTP. So the one-time password is the 6-digit number from your phone. So there's a question about what should the path refer to when typed in a browser. So this is the bit that I'm going to show you next. To go back to the documentation. So please skip this if you're connecting from a Windows machine. But I'm not connecting from Windows machine. So it's a similar kind of setup with Windows and Linux, but I'll show you the Mac version. What you need to do now is create a tunnel between your laptop or whatever machine you're working on locally in front of you and the Archer login node, because you're going to use your browser on your machine. The server is running on the login node, so you now need to make a connection between the two, which is what we're going to do next. And you do that with a command like this from the documentation. And let's fill in the details now. So my username is and then it asks for a port number, and this port number is the one you get from, it's shown in a couple of places here, 8892. 8892. It'll depend on who's using what, but so everyone will probably, you'll get a unique port on a given node ID. So I'm going to connect to 8892. My node ID is LN02. It's login node 02. It's the one that I'm running on. And I put the same port number in here. And I've got multiple keys, so I still need the -I flag that I used before. asking for a passphrase. And once that terminal opens, the tunnel is established. So you don't need to do anything else in this terminal. You should now be able to open your web browser of choice and copy and paste in this line here. And in a moment, it's maybe a little bit busy with everyone running, it will open the Jupyter Notebook interface. Yeah, okay, so Omar, the permission denied message is because you've typed the password exactly as shown with work T01. T01 needs to be, so if you type your, if you type CD and then BWD, that'll show you your work, where your things are. You need to change home to work. So I think your one will look something like /work/TA followed by a number. I think the training accounts are TA followed by a number, /TA with a number again, / and then your username, which may also start TA, but you can see this part is exactly the same as what you get from your home directory. Sarah is getting a no problem, Omar. Sorry, maybe if it wasn't clear. Yeah, so that part of the instruction, it has to match your work directory. So Sarah, it is saying permission denied public key. So again, so the things to check, first of all, make sure that your public key has been uploaded into safe. As long as your public key has been uploaded into safe correctly, then the next thing to do is to check that it's finding the right key. So you can either use the -I flag to, so when I connect using SSH, I put in this -I, and it's telling it directly the location of the key, which is in my SSH directory. I've got oh, I'm on Archer, so that's why it's empty. On my laptop, I've got multiple keys for connecting to different machines, so that's why I specify the -I flag. It should work anyway, but experience tells me to explicitly specify the key with -I. Which password is the LDAP password? Yeah, okay, so Aaron, I think Nathan's answered your question. John, you're using Windows Subsystem for Linux. What steps do I need to take to connect to the browser window? Do I need to run a browser from within WSL to do so? No, so what you need to do is so you first of all have a terminal connection to Archer where you start the server, which is what I did here. Then you will need another window where you have where you typed in where you made the tunnel. So that's the one where I had the it looked a bit like this, where you're making a connection between your local machine and the login node on Archer, where you've run the server. So those two steps are similar. So you'll have one window where you've started the server, then you make the tunnel in another window, and then you just paste this URL. Use the bottom one, don't use the top one. Your laptop doesn't know what LNO2 is. It does by going to 127.0.0.1, that is your local, that's called local host. So it's trying to connect to your own machine on tunnel 8892, on port 8892, but you've already set up a tunnel so that when you try to connect to port 8892 on your local machine, it tunnels it through to the login node. So this URL, you put in a browser window running on your local machine. So for me, it's Safari. For you, it might be Edge. It doesn't have to be in WSL. It can be anything running on your machine, and it should work. All right, Aaron, sorry to hear that it's always annoying things like that that get in the way. Yeah, classic. Copy and paste. Glad to hear you're connected. Okay, so I mean, the whole point really of this first practical is just to check you can connect and do these things. So don't worry too much. You put the wrong node in, and it was worried it was an issue with running Firefox and Windows was WSL. No, okay, yeah, no. So it's yeah, so it needs to be your log. It needs to be the login node, LN0 thing that needs to be picked out from wherever you first connected. It's like it's a bit of a chain. It's really weird the first time you do it because it doesn't seem to make a lot of sense. But but over time it becomes fairly second nature. So you're connecting, you're building the tunnel, and then you can connect to the tunnel from your local machine and do all the notebook things locally. So the remote server is login.archer2.ac.uk. Remote port, you should be able to leave as default. It's the standard SSH port, which I can't remember off the top of my head, but it should be. Is there a number in there, a default? You should just be able to use the default SSH port. Probably 22. Right, so Aaron, yeah, I don't know if you're using your normal Archer account or just the training account. If it's a training account, things will be empty when you start anyway. To get to the course, if you want to get copies of the notebooks and so on from the course materials, at the bottom of this, the first practical exercise, the easiest way to get the notebooks for practicals for the rest of this course is to clone this repository directly onto ARCHER2 with this command. So you should be able to get the files there. After tunneling, when I tried to connect to the server from the browser, the site can't be reached. 127001 refused to connect. So the next step I would take there, Aaron, is to look in the window where you set up the tunnel and see if there was an error message when it set up the tunnel. Sometimes it can still go to the login prompt, even if there was an error with setting up the tunnel. If there was no error message, then we might have to troubleshoot further. Site can be reached. 127001 refused to connect. And you did. Yeah, okay, and so there are two places you could look. You could look in the window where you created the tunnel to see if there were any errors when the tunnel was created. You can also look in the window where you first started the Jupyter server, the Jupyter Lab server. There may be error messages there. If there's nothing obvious, my suggestion would be to restart the server and to recreate the tunnel and try again in case something has gone wrong. I'm going to leave that there just now, Aaron, and move on with the next lecture, but hopefully we can pick that up in the next practical session if you're still having connection problems. Okay, so the next lecture is an introduction to machine learning, and then after that there's another lecture on linear regression. So I'm afraid you're sick of my voice, but this next session you really need to get a bit of background information before you can do some of the practicals. So let's embark on the next couple of lectures. So an introduction to machine learning. As with the previous talk, it's going to be a bit of a whistle-stop tour, but hopefully I can convey some of the important ideas behind machine learning. So what is machine learning? Different people have different definitions, but basically it's getting a computer to do something without explaining to the computer exactly how to do it. So we're very used to, in the past, the way you get a computer to do something for you is to write a program step by step, with each line telling it the precise order of things to go through. So if you are you have to write the code which explains exactly what you want the computer to do. The idea behind machine learning is that you're trying to get the computer to do something without explaining exactly how to do it. So there's different kind of ways you can do that. The classic one is learn from these examples. So what I'm going to do is I'm not going to tell you how to recognize a picture of a cat or a dog. I'm not going to tell you what the features that a cat has to look for or the features that a dog has to look for. I'm not going to program anything about cats and dogs. All I'm going to do is give you lots of examples and say, look, this is a cat, this is a dog, this is a dog, this is a dog, this is a cat. And once you have seen lots of examples of cats and dogs, you'll become pretty good at learning what a cat is and what a dog is. And I've not had to explain that the eyes are different, or the whiskers are different, or the shape of the head is different. All I've done is given examples. And that is one way that machine learning works. And this example of giving examples of things is called supervised learning. Another approach is to give it the data and say, find patterns in this data. So you're not telling it to look for something specific. You're telling it to look for patterns. So in this case, the example might be, well, given information about all of your customers, can you group your customers into sets that are in some respects similar? And then maybe you could treat them as a particular group together in a marketing campaign or something like that. So you're looking for patterns. You're looking for groups, clusters, or different kinds of patterns. And that kind of machine learning is called unsupervised learning. There is another kind of machine learning which is trying to achieve, so you tell the computer, try to achieve this goal by learning from your experience. And that is called reinforcement learning. So in that case, you specify what the goal is, you specify some things. You maybe teach a robot, you could say, well, this is how you put move one leg forward. This is how you move one leg back. It's over to you. Try out moving your legs in different directions, in different speeds, in different combinations, until you can get over that rock over there and learn by your experience. That is reinforcement learning. So these are the three most common kinds of machine learning. In fact, supervised learning and unsupervised learning are probably quite a long way the most common. But in all of these cases, the idea is that you don't explain exactly how to the computer to do something. You don't give it an explicit program. You give it instead data, or you allow it to experience the world by getting its own data through sensors or something in the case of reinforcement learning. And that is the way that you teach it to do something. So it's getting a computer to do something without explaining exactly how to do it. Why is it so powerful? So as I've touched on this already, you can basically use the same algorithms for tasks in multiple domains. So whether that's identifying genes that are similar to each other or identifying customers that are similar to each other, it's the same kind of algorithm. Predicting which of your customers are likely to unsubscribe from your service and predicting upcoming weather from current rain radar images, same kind of algorithm, because it's just predict from a given set of data. Identifying tumors in medical images and identifying specific words spoken to a voice assistant like Alexa or Siri. It's a vastly different domain. In this case, different kind of data. One is an image and one is voice. But the algorithm for looking for similarities can be the same in each case. Classifying images of dogs and cats, or classifying email as spam or not spam. This is a classification problem. In this case, both are binary classification because you've only got two choices. So it's the same algorithm. Okay, you've got to pre-process your images slightly differently from how you might pre-process your email. But once you've got that into the right shape, you can use the same machine learning algorithm to do the classification. Teaching a robot to walk and predicting the next word you will type in a text message might not seem like the same kind of problem, but ultimately it's sort of learning from experience. Teaching a robot to walk, it'll work out which movements lead to it achieving its goal. Predicting the next word you will type in a message is the same kind of thing, because the phone will learn which words that you tend to type next. So it can offer predictions, and it can decide, it can see whether you accept those predictions or whether you type other words. So it learns from the experience of you typing. More recently, responding to a prompt in ChatGPT and creating an image from a text prompt. These are both things that use transformer models, which is something we'll only just touch on right at the end of the course, because it takes a while to get there. But it's the same kind of algorithms in this case. Again, difference in the detail, but the same algorithms, basically transformers used for the text in ChatGPT and for image creation in the case of these automatic image generators like DALL-E and so on. So here are some other definitions of machine learning. Hopefully they will match up kind of what I was talking about before. Machine learning is the field of study that gives computers the ability to learn without explicitly being programmed. This is possibly a paraphrase, but it's widely accepted that the term was coined by Arthur Samuel around 1959. It's difficult to find the exact quote, but this is sort of the idea of learning without explicitly being programmed can probably date back to about that point. Machine learning is a field of study in AI concerned with the development and study of statistical algorithms that can effectively generalize and thus perform tasks without explicit instructions. So you've got the tasks without explicit instructions again, generalization and statistics. That's because we're doing modeling of a kind, and learning from the data and learning from example is a kind of statistical type problem. Machine learning is a branch of artificial intelligence and computer science which focuses on the use of data and algorithms to imitate the way that humans learn, gradually improving its accuracy. So, and again, Andrew Ng from Stanford and Coursera fame says it's the science of getting computers to learn without being explicitly programmed. So, similar definitions. The imitating the way humans learn is an interesting one because some aspects, you can see the inspiration there, but even when you get onto neural networks, you can see that it's the human brain that has inspired the network rather than the artificial neural network actually being a realistic model of how a human or any other kind of brain works. So it's sort of similar in principle, but different in detail. But so inspired by the way humans learn would be better than imitating the way that humans learn. So what then do machines learn? Central to the machine learning is the idea of a model. The model is learned from the data using some kind of machine learning algorithm. So there's still an algorithm here, but it's not an algorithm of how to recognize a cat. What the algorithm is, it's an algorithm of how to classify something given an example. So that's what the machine learning algorithm is. It tells all you say to the computer is, this is how you classify something given examples. So the model is learned using a machine learning algorithm, and then that model can then be used to make predictions or classifications from new, previously unseen data, in the case of supervised learning, or to cluster or group the data in the case of unsupervised learning, or to decide on a course of action in an observed environment in the case of reinforcement learning. So the model is key to what machine learning does. The machine learning algorithm is used to learn a model from data, and then that model is used to make a prediction or to decide on a course of action or to find a pattern in the data. Generally speaking, with machine learning, machines do not learn facts, and they do not learn to reason. They learn models and patterns. There's no reason why this isn't possible in future, in principle, but that's not how machine learning currently works, even when it looks like it's doing that in the case of ChatGPT. So even ChatGPT at the moment is not really learning facts. It is certainly not learning to reason. It's learning models and patterns. So machine learning can be broken down to this kind of hierarchy with unsupervised learning, supervised learning, reinforcement learning. Then there's things like semi-supervised learning, and probably some even more strange ones off to the side over here. But the main 2 or 3 are these 3. And then, so these, as hopefully you've picked up, these are about sort of different problems. This is sort of learning from experience. This is learning by example. And this is looking for a pattern. And then within that, you can do different kinds of things. So unsupervised learning might involve clustering, so grouping things together. It might also involve things like anomaly detection, for example. So that's kind of like identifying things that are not in a cluster. Supervised learning, the 2 most common types of supervised learning are classification and regression. So classification is about identifying the class of something, what kind of thing it is. Is it a cat? Is it a dog? Is it spam? Is it not spam? Regression is about finding a number, as I'm sure many of you are aware. So continuous value. So what is the temperature likely to be, or what is the number of customers that I expect to get given a certain input. So yeah, so these are kind of broken down as to whether you're looking for classes or whether you're looking for continuous values. Then within, for example, clustering, there are different algorithms, different machine learning algorithms that are used for doing clustering. So you could use something like k-means, you could use something like dbScan, or hierarchical clustering. I'll talk about some of these later as we go through the course. In supervised learning, some of the most common algorithms with regression is linear regression. There's other kinds of regression as well. For classification, some of the common ones are k-nearest neighbors, naive Bayes, logistic regression, which despite its name is a classification algorithm and not a regression algorithm. Basically, what it does is to draw a line, regression style, but then to classify something, it says, well, if you're on one side of the line, you're in this class, and if you're on the other side of the line, you're in that class. So a bit of a false, a bit of a confusing one there, but that's another classification algorithm. And neural networks, as we'll come on to tomorrow, in particular deep neural networks, are commonly used these days for classification as well. So these 4 diagrams here are sort of trying to show how all of these things fit together. So in most cases, when I looked online at trying to see what people's definitions of how these things fit together, almost universally now you get this kind of hierarchy where they say artificial intelligence includes everything. Machine learning is a subset of artificial intelligence, and deep learning is a subset of machine learning. So not all machine learning is deep learning, not all artificial intelligence is machine learning. So this is what you'll widely see online, which is broadly correct. But I would say there's probably maybe a little bit of a slight oversimplification. In particular, I would say that machine learning, not all machine learning really has an artificial intelligence application. Some people now just consider it all a kind of artificial intelligence, even if you're sort of looking for patterns in your company database or something, and you're still doing this with quite a human, an iterative human approach that you might use in traditional data mining or knowledge discovery in databases. So I would say that I wouldn't have originally called this AI. And so I would argue that there's a bit of machine learning that isn't really AI in the traditional sense, but most of it is these days. Similarly, there are parts of AI which are captured by the original diagram that are not really machine learning. So things like the ethical aspects of it, maybe more old-fashioned. Some of the earlier attempts at AI were based around expert systems or rule-based systems. And these are not really to do with machine learning at all. And there are also things like natural language processing, NLP, written here, which are basically done with neural networks or machine learning, but there are certain aspects, specific aspects to NLP about how you prepare the data and things like this, which are probably not machine learning themselves. They're sort of prerequisites to it. So I kind of agree with this diagram mostly, but I would say that there's probably some machine learning which originally would not have been called AI. So the next lecture is going to be on linear regression as an example of machine learning. So many of you will, I'm sure you will have done linear regression at some point in your life, finding the line of best fit through lots of points. And this, of course, was being done long before this was considered a kind of machine learning. But it is essentially, it's got all the same elements that machine learning involves, and it is an example of basic machine learning. And so we're going to cover it first because it covers a lot of the key points that you have to understand when you're understanding how machine learning algorithms work. So it's a kind of, why is this an example of machine learning? Well, given a new value of data, so first of all, okay, given a new value of data point with known X but unknown Y, can we predict Y? So this is a predictive model. Given some existing data and now a new point, can we predict something about the new point? So that's a classic regression, a classic machine learning kind of problem. The model here is the red line, the line of best fit. So this is what we're trying to get the machine to learn the model. The model is learned using a process which finds the best fit for the existing data points, which we refer to in machine learning terms as the training data. But it is, so you've got existing data, the blue circle points on this graph, and you've got a line of best fit, the red line, which is the model. So when we try to fit the model to the training data, or when we train the model using the training data, both of these words are used, what we're trying to do is to find the best place to put this red line, given the existing data, so that we can use this red line in future to predict new values of Y over here. So it illustrates the idea of fitting, of training. It shows training data, the existing blue dots. It shows the idea of a model, the red line here, that we're trying to learn. And another key point is that in machine learning, like here, we often decide on the shape of the model. So we, as the humans, the programmers, decide, okay, we're going to choose a straight line to represent this data. But then we let the machine learning algorithm find what the best straight line is. So we tell it something about the model, very little, really. We're just telling it, okay, in this case, we want a straight line model, and here's the training data. Tell me what the best model is for this data. So a few more general points before we get into some of the specific algorithms. Models are only as good as the data they're trained on. This is probably obvious, but it's often overlooked. So we have the possibility for bias, either conscious or unconscious. The training data does not represent the population that you are actually trying to reason about or make predictions about in the future. And also, even if it did represent the situation in the past, there's the possibility for changing underlying conditions. Quite a number of machine learning models broke during COVID because the expectations of how things were related to each other no longer held true. So models are only as good as the data they're trained on. And in particular, rare events can be harder to model with machine learning. That's a sort of special subfield of people who are particularly interested in predicting rare events. But generally speaking, these are harder to model because there's less training data. Machine learning models tend to be fairly opaque. It's difficult to understand why they make a certain prediction. It's the computer says no type element of these things. We know even if we know how neural network is trained and so on, what we cannot get out from the model is an explanation of why it has made a certain prediction. So explainable machine learning, again, is a sort of field of study that people are trying to look for ways, different kinds of models or ways to interpret models so that we can be better at understanding why they make a certain prediction. But often the answer is simply, well, statistically, based on the examples that you've shown me, this is the answer that is most likely to be true. And you can't get any more insight. Another thing to keep in mind as we go through that there are different ways of deciding if your model is good. So if you have your artificial intelligence poisonous mushroom detector, are you more concerned as to whether it is how accurate it is? Say you want it to be 98% accurate, or would you be happy if it was only 95% accurate, but it erred on the safe side when it wasn't sure, so that you never accidentally picked and ate a poisonous mushroom? So there are many situations where you've got to think about what the right definition of a good model is. So with linear regression, it's almost universally a least squares fit that's used. It doesn't have to be. You can have other definitions of what makes the best straight line. Finally, training models is often computationally expensive. So finding that model takes a lot of computation work. Okay, can everyone hear me okay? Rondro has created the sound. Most people can hear fine. I'm afraid, Rondro, it looks like it might just be you. Things are all looking fine from my side. Okay, so yeah, training models is often computationally expensive. Modern computing resources make this more accessible than ever. And training is usually much more resource intensive than prediction and inference. So that is why quite often you would need a data center or a supercomputer to train your model. But once you've got it, you can put it on a mobile phone and it can sit there in the background and work out who's in all of your photos or something like that. So these are things to keep in mind as we're going through the actual details of the algorithms. When it comes to training models, when it comes to coming up with these models, as we'll see, the process of training these models is often iterative. That's to say that machine learning algorithms often repeatedly use the training data to get better and better models, as we've discussed, for some definition of better. And generally speaking, this is a trade-off. The longer you train, the better models you can obtain. Not always the case, but generally speaking, that's true. Stephanie, yes?
Does that mean that they use the same training data over and over again, or do they use new training data and train with the new data?
That's a good question. They can improve even using the same data over and over again. Either because they're using, because the process is just iterative and that's how they work. Or you can explicitly do things. If you've only got a small data set, there are things, or an unbalanced data set, you can use approaches called data augmentation, where you take your small data set and generate from that other examples. One classic example might be images that you're trying to classify. If you've only got 100 images, but then you can also rotate them or put a different color filter on them or something like that, you can increase the number of training images. But generally speaking, what I'm getting at here is that, yes, you can use the same data and just keep training the algorithm on that same data. And normally that will improve the model. Yin?
Yes, if we can use the same training data and yet it gives us a different model, does it mean that machine learning is not reproducible?
Another very good question. So these are statistical things. So can it give you a different answer each time? The answer is yes, but normally only if you. But the algorithms, the machine learning algorithms, have random number generators in them. And if you seed your random number generator in the same way that you would for any statistical process, if you fix the starting point of your random number generator, in principle, the results are repeatable, and you can get exactly the same answers. In practice, particularly the way the algorithms scale, and you've got some, if you're doing a sort of distributed or parallel type algorithm where you're not necessarily training in exactly the same order, so you can't be sure that your random numbers will come out in exactly the same order. It won't give you exactly the same answer out at the end. So it's statistical in a way that I don't know, Monte Carlo model might be as well. So you won't always get, they can be difficult to replicate and to get precisely the same answer out. In principle, you want these to be trained for long enough and the model to be robust enough that the predictions it gives will be consistent, or at least within a certain margin, even if you were to train it multiple times. So it can be difficult to reproduce, but it's the same kind of reproducibility issues that you would have with, say, a Monte Carlo model. If you use a seeded random number generator and you can make sure that your algorithm is one where those numbers always appear in the same order, then in principle you can get exactly reproducible outcomes. So one of the things, so we did talk about reusing the same data over and over again when you're training the models. One thing that can go wrong is, particularly if you try to do this for too long, you can build a model which suffers from overfitting. In this case, you end up with a model that represents the training data very well, but does not generalize to new unseen data. So if you can imagine, Sam, I'll come to you in just a moment. if you can imagine that overfitting this data, you might get some kind of line that goes up and down, and you can try and get it to go through all of these blue points or many of them, and it would sort of show these oscillations and so on. And so if you looked at it, it would your model would be forced. I mean, it wouldn't be a straight line model in this case, but if you had more degrees of freedom in the training that you might get from a neural network or something, you would end up with a model that overfit this data and kind of found a pattern in the data which was really just the randomness. So it's too close to the training data and not generalizable. Can be a challenge. There are approaches to dealing with that, and that issue is called overfitting. Sam, you had a question.
Hiya. So is this why you're saying that a good way of making better models is to have more data? Because if you have more data, then your chance of seeing any unseen data in the future is less likely because you have more from the start, and so overfitting becomes less of a problem.
That's very much, yeah, that's certainly the case. Yes, if you train with a small data set, it's more prone to overfitting. A larger data set, you can still have bias. You can still have a large data set that is not representative of the population that you're trying to model. But in general, a larger amount of data will give you more examples. It will cover more of the training cases. So one thing we'll talk about a little bit later on, that's maybe worth mentioning here, is that a straight line in 2 dimensions is defined by 2 parameters, the slope and the intercept. So they're called parameters. And so with this kind of model, there aren't many parameters that you have to tune, that you have to learn to define the model. The more parameters that you have, the more data that you really need, if you're thinking like in terms of degrees of freedom or something, to correctly pin down all of the parameters of your model, the more data you have, the better, because it'll help you get a model which more accurately is it's generalizable, and it can be used more widely in a predictive way. But to answer your original question, yes, you're right. The advantage of having more data is that it allows the model to be more representative and have more predictive power, assuming your input data is good. Okay, so where are we in terms of time? Well, I'm already a little bit overshooting. Right, so I will thank you for the questions as we go through, but hopefully that gives you some sort of examples of what machine learning is about at a high level and what some of the important things to look out for are. And we're now going to dive into some of the specific examples. So let me just find the next slide set. And share the screen again. Good. Okay, so we'll go back now and talk about linear regression. It's not the 1st of September 2020, but everything else is correct. So we'll use this first, probably because it's an example that you're hopefully familiar with, but also because it highlights many of exactly the same things that we'll talk about when we come on to things like neural networks. So the purpose of this specific talk is here as a way to introduce concepts in machine learning, such as models and optimization and cost functions and distance metrics. It's secondarily to describe how linear regression works. So we're not going to go into a big statistical linear regression from a statistics point of view. We're going to use it as an example of machine learning. And we'll also, in this talk, introduce a little bit of mathematical notation that's often used in the field. I'm hoping that most of you will be comfortable with a bit of mathematical notation. If you've got any questions, just let me know. So, yeah, this slightly different colors in this, but the hierarchy is the same. So we're going down. This is an example of supervised learning. This is an example of regression, and we're going to focus on linear regression here. So linear regression predicts a continuous variable from one or more other variables. It's one of the simplest predictive models, and the existing data is used to create a linear model, as we saw before. So the model is going to be a straight line. So one classic example that's often given, I'm trying to work out what the price of a house is going to be given its size in square meters. So here are some examples. It goes up. So this, times 10 to the 6. I thought it was very cheap houses there for a moment. But given my size in square meters, what's the price of the house? And you can see, first of all, okay, it's not unreasonable to use a linear model here. It doesn't look exactly linear, but our exploratory data analysis, our plotting of the points, tells us that it's probably a reasonable place to start. Another important aspect of sort of machine learning in general is the feature selection. In this case, is the size of the house actually the most important thing to use when predicting its value? Maybe it would make more sense to use the number of bedrooms, or maybe it would make sense to use the location somehow, or some other aspect, some other feature of the house. But in this case, just given the size, we're going to try to predict the price. So there we put a straight line through the data, and that is the model. And then from that model, if we now had a new unseen piece of data, if we now know that our house is 84 square meters, I'm going to put it on the market. What kind of price might I expect to get for something that is 84 square meters? So I'd read up here, and I can read off the value for the price of the house. So the red line here is the model. The unseen data is this one that we were trying to predict here. This, in this case, is the training set inside the blue box, and we had this piece of unseen data here. So this is a classic example of supervised learning, in that we have some kind of training set. We then put it through a learning algorithm, in this case, a least squares fit linear regression. And we come out of that, we get out of it a model. And here the model is represented by the equation of a straight line with two parameters. We've got some number that multiplied by the size, so that gives the slope, and this gives the intercept. So in this case, we've got a two-parameter model. And then when we want to make a future prediction, we take that new piece of data, we apply the model. We don't need to keep in mind here any of the original training set. We just keep the model, and that gives us a prediction for the price of the new of the unseen data. So a little bit of notation, just so you can see. So I'll probably use this in some of the latest slides. We often say that there are M training examples, so that's M rows. N is the number of features, so the number of columns, or the number of columns from which we are predicting normally. Again, different people use slightly different convention, but here N equals 1 because we're predicting the price from a single feature. X is used to represent the input variables or the features. Y is usually used to represent the output or the target variable or the feature. So variable is a little bit more of a statistics-y type name. Feature is a little bit more of a machine learning-y type name, but they're basically the same thing. X, Y is used to denote a single training example. So one row, so it's a pair of an X value and a Y value. This notation here with an I in brackets in a superscript is normally used to represent a particular training example. So in this case, the ith training example. The subscripts are normally reserved for something else, which we'll see later on. So that's why we use this superscript notation, and the brackets are just there to help clarify that we're not raising anything to a power. It's just another index into the value. And we'll often see a hypothesis function labeled H subscript theta of X. So, and the thetas are then the parameters. So the equation of a straight line, we have some hypothesis function. So our guess is the value of X is given by some parameter theta naught plus theta 1 times X. Here M is 5 because we've got 5 training examples. Here the price is a function of one feature, so N equals 1. So we choose our hypothesis function to be a linear function with one variable X. That is the equation of a straight line with linear with y-intercept theta naught and slope theta 1. Once we find the optimal parameters, once we find our values of theta, this function will represent the model. So models like this are sometimes referred to as parameterized models. Nearly every machine learning model is some kind of parameterized model, and we choose the general form of the model, and the computer learns the parameters. So we have 2 parameters here. Deep neural networks can have millions, as we'll see. So given our hypothesis function, given our best guess as to what the shape of the model should be, how do we find the thetas? How do we train the model? How do we fit the model? So we want H sub theta of X as close to Y as possible. So the value that we get on our training data when we apply the hypothesis function should come out to be as close as possible to the actual value of Y in the training data. So H as close to Y as possible. Another way of looking at that is we say, well, we want H minus Y to be as small as possible. So we define something called a cost function, which depends on the parameters. And this is a measure of how far away the hypothesis function is from the measured values of the target variable in the training set. Before I look at the equation, let's go back here a minute. What we're doing here is we're kind of summing up how far away all of these blue training points are from our current best guess of the model. So given some values of theta, what is the cost, what is the total distance if I sum up all the points, and I'm summing up the distance of the point from the line. So this is the point, actually, this is the line, but the difference between these two, and y square, well, for a start, in this case, we don't care whether it's above or below, the point's above or below the line. And so we're trying to find something close to 0. So if we could minimize the absolute value, but the common thing to do is to minimize the square. And why a 1 over 2m here? Well, there's sort of a normalization thing. I'll explain maybe a little bit later on where the 2 comes from. But this is basically just saying we want the total sum of the squares, that's why it's a least squares fit, to be as small as possible. And for least squares fit and linear regression, this is the cost function. So this is the general concept that I'm trying to get across here, is the cost function, because nearly every new, machine learning algorithm will have a cost function. So note that we can choose the cost function here. Simple linear regression usually implies that we're minimizing the mean square error, but we could equally minimize the absolute value, for example. That's a different cost function. It would give a slightly different fit. And the point of what we're trying to do is, once we create a cost function which measures the distance between the blue points and the red line, what we have to then do is minimize the cost function. So that is, we need to find the values of θ0 and θ1 for which this is smallest. So this is a simplified example. Imagine a case where our training set values fall exactly on the line y equals x. So it's a little bit artificial, but that's what we've got here. The red crosses, hope you can see them, fall exactly on the blue line, which represents y equals x. So we're going to start off by assuming that θ0 is 0 and and h is θ1 of x. So here the hypothesis function h is passing through 0, 0, and the choice for θ1 controls the slope of the straight line. So let's consider the case where we initially chose θ1, the slope, to be a half. The cost function here, this is just an example of how we would calculate the cost function. So every different possible line here, green line or any other slope that we wanted to put on this, you could calculate the cost function. So if this was our initial guess, we plug in the numbers and we would get the value 3.5 out. So for our initial guess, we get a value of 3.5 for the cost function. And we can clearly do better than this. So, but how do we go from our first guess to our next guess when we're trying to minimize the cost function? So for this very specific example, we're now going to look at how j θ1 varies as a function of θ1. So in this specific case of a very somewhat artificial model, we can measure how j θ1 varies as a function of θ1. So here's our value of j θ1, and in our case, the training set, the target variables y are given by the equation y equals x. So we can substitute this in here, and we can substitute a hypothesis function into the usual expression for the cost function, and then we can work it all out. So this now gives us j of theta as a function of theta, and we can plot that, and it just looks like it's a parabola. It's a function of θ1, and we can see that there is some minimum value of theta where this cost function is minimized. So that would be the best, the value of theta that would give the best fit. So given that we have a way to calculate our cost function for any value of the parameters, how do we minimize the cost function? So this is another key point to what all of these algorithms are doing, you're minimizing a cost function. And the next point is that there are many different optimization algorithms that you can use to do this. And this is often a choice that you have when you're doing machine learning. The most common approach is to use a version of iterative gradient descent algorithm. I think I've got a few slides on the gradient descent algorithm coming up. Yes, I do. And there are various variations on this. One called batch gradient descent, which uses all of the training examples. Stochastic gradient descent, which uses one example at random, which is why it's stochastic, in each iteration. Another one sort of in between called a mini batch gradient descent, where we use B examples. So we use a subset of the data at each iteration. So gradient descent algorithms are very common, and then there are sort of variations on the gradient descent algorithm. So this is all about how we find the minimum point in some cost function. So iterative methods like gradient descent are common in machine learning algorithms, including, for example, neural networks. In some rare cases, and actually linear regression is an example of one of these, so unlike most other machine learning algorithms, it is possible to find an exact solution analytically, given the training data. For linear regression, the parameters can be found exactly using something called the normal equation. In practice, well, I suppose it depends on the number of points or what you're doing it for. But so for linear regression, you can work it out exactly, but nearly every other case, the way you find this point at the bottom, because you can get more complicated shapes, is to use some kind of iterative algorithm. So gradient descent with one parameter. If we start here, the idea is that it's called gradient descent because we start here, we find out what the value of j and the slope at this point is. And because we've got the slope, we now move in the direction of the slope to pick our next value of theta. So if you go back to the house prices, that's how, given one guess, we can improve our guess as to where to go next. If we start here on the other side, we would move in that direction because dj by d theta is negative. If we start there at the bottom, if we happen to be lucky, we would stay there because the derivative is 0. So it's an iterative algorithm to find the best value of theta. We take the existing one and we move in the direction of the slope by some value which is proportional to the gradient. Yes, Sam.
Is this susceptible to finding like a local minimum in certain scenarios, and it can't find like the actual global minimum?
Yep. So in this case, nice least squares fit for linear regression. You're going to generally you get a parabolic shape, so you will always find the global minimum. But in the general case of a general model, say for a complicated model with many parameters on a neural network, yes, you can find global minima, and that can be a problem.
So it works here because our cost function is kind of built to be a parabola, right?
Yeah, so the choice of the cost function is important in trying to find one that will converge on the global minimum. In practice, in machine learning, if you don't find the global minimum, it tends not to be catastrophic, because a local minimum, what that means is that in most cases, you get a model that predicts most values well. And these things are sort of, because there's some noise in the data anyway, and it's an imprecise model, normally a local minimum, or often a local minimum, will be sufficient. But yes, it can be a risk, as with any iterative minimization thing, and it's one of the reasons that people keep trying to come up with better optimization algorithms. One is for speed, one is to make sure that you don't get stuck in local minima. In machine learning, this value of alpha here is known as the learning rate. And this is an example of something called a hyperparameter. So the thetas are the parameters. These are the things we're trying to learn. Hyperparameters are these things that we can tweak and control to try to, as efficiently as possible, learn our model. In this case, a larger alpha can lead you to faster learning. You get to the minimum more quickly, but it can allow you to overshoot the minimum. In this case, a smaller alpha leads to slower learning, but makes it easier to converge on the actual value. Our different algorithms, some of them are a bit more complicated and they don't have a fixed learning rate. They decrease the learning rate as you get closer to the actual value. But the principle here is the same, that you've got and again, we'll come back to this with machine learning. It's all about the slope. It's all about the derivative of a cost function with respect to the parameters. That's what we're trying to minimize. And that's what happens in a neural network as well, is that you're minimizing some cost function with respect to the parameters. More generally, linear regression involves solving for multiple dimensions, multiple features, to minimize a cost function of many variables. And the process, in general, we repeat the following step until convergence, and we simultaneously update all the different values of theta. We've got a partial derivative now, but that's just because your slope is now in a multidimensional space. We've only got two parameters here represented, because that's about as good as I can picture on paper or a screen or in my mind. But in principle, remember, we're doing many features. So we're doing this minimization over many multiple dimensions, but the same algorithms can be used. The same maths works. You're just looking for a slope in a particular direction in this multidimensional space. In this case, as you just mentioned, this case of linear regression, even in multiple dimensions, J of theta is always convex, so there are local minima. As you've pointed out, for more complicated models, this is not always true. Right, do we really need all of this maths? How are we doing for time? We've still got a bit of time, so let's dig into a little bit of it. So to perform this update, we need dj by d theta j for all j. So in the general case, we've got a partial derivative here. And now what we're doing, now we're actually plugging in our cost function. We're taking the derivative of the cost function in order to find the slope. And we're then trying to set this, we're trying to find the point where the derivative is equal to 0, because the minimum comes when the slope is 0. So we're trying to do the derivative of this expression here, partial derivative, because we're doing it one direction at a time. I said I would point out where the 2 comes from in the cost function. That is there as a convenience. It doesn't matter when you're minimizing it. Half of it, twice it, whatever thing you've got in the front, it doesn't matter for minimization. But for doing the maths inside a computer, when you take the derivative of something squared, as usual, the 2 comes down and cancels with the 2 over here, so that it cancels out, and in the calculation of the cost function, there's no number to multiply or divide by at all, which makes it computationally cheaper. So that's why the 2 appears in the cost function, because when you take the derivative of the cost function, they cancel out. So this is just the different steps. What do I need you to see here? So what we're doing is we're calculating the cost function. We're putting this back in now into the update equation that we had, and substituting back into the gradient descent update function gives something like this. So what we're doing, so that we no longer have the derivative in here. We've actually worked out what the derivative is and put that back into the update equation, so that we can always find, given any point, we can always work out what our next point will be. Sam, yes, you had a question.
The bottom line should be theta 1 is defined as theta 1 minus alpha blah blah blah, right? Not theta 0.
So the bottom line here.
The bottom line at the end of this slide, yeah.
It should indeed be theta 1.
Okay, gotcha.
Apologies. Well spotted. Yeah, this one comes from this line. When we did the derivative with respect to theta 0, there's no theta x because we've taken the derivative of a constant, so there's no x. In the case of something where there was an x squared, you end up with an x. So correct. This is the update function for theta 0, and this is the update function for theta 1. To update it on GitLab, but for just now. Okay, there we go. So that's the end of the maths for that just now, at least. Don't worry if you didn't follow all of that. The key point is that what we're often trying to do is calculate a derivative of a cost function. It's all about minimizing a cost function by calculating the derivative of a cost function. So just before I move on to the next slide, there's kind of 2 ways you can think of what a derivative means. You can think of it as a slope, which is what these minimization algorithms are trying to do. We're trying to minimize the slope. We're trying to get a flat slope so that we know we're at the bottom. The other way to think about a derivative is, how does one variable change when you change another variable? Maybe that's obvious, but another reason why this might come in important when it comes to neural networks and so on. What we're ultimately trying to think about is, how does the output of the neural network change when you change the input? Or what kind of changes to the input do I need to make to get the value of the output that I want? So you can kind of see already why knowing derivatives is a useful thing of being able to connect an input of something to an output of something. How do we choose this learning rate, this hyperparameter? We want the cost function to decrease after each iteration. So the number of iterations until it converges can vary a lot. So one thing we can do is to plot the cost function against a number of different iterations, or we could also do some kind of automatic convergence test and decide that we are happy if the cost function decreases by less than a certain amount in a given iteration. If it doesn't converge, you might need to use a smaller alpha. The most common cause for increasing cost function, like if you're trying to train your data set, trying to train your model, your neural networks, for example, and it's not converging, and you're getting a value where the cost function is actually increasing as you're trying to train it. This is normally because a learning rate, some hyperparameter, is too large. So for linear regression, you might choose these values and plot J against the number of iterations, and then find one which is not too small. So as you can see, this bit is fairly experimental. You really just got to try it and see. It's quite hard to choose hyperparameters. There's a little bit of an art to it. In some cases, there are specific ways, specific processes that have been worked out for doing this in an efficient way. But generally speaking, this is one of the tricky things to do with machine learning, is to choose your hyperparameters. Yes, question. Sam.
Sorry. So at the end there, you said that you try different values for alpha. Is there any thing, because this is an iterative process, right? If you could start off with a larger value of alpha, is there any processes where you slowly decrease alpha down to 0?
There certainly
you
are.
don't have to
They're quite common. So there is approach. Let me just see. So there's another optimization thing called ADAM, which stands for adaptive. I can't remember what it stands for now. That adaptive moment estimation. That does a little bit more than. So there's different ways you can improve on it. You can have your learning rate that changes as you go through. ADAM actually does something else as well, where it considers higher derivatives. So it doesn't just look at the slope, it looks at the second derivative of how quickly the slope is changing. And by also taking into account how quickly the slope is changing, it can adapt the learning rate alpha as it goes. So by also looking at the second derivative, you can change your value of alpha as you go. And there are various different techniques that are used to do optimization in different ways, but the principle is similar. Gudrun, I recently got the question, you optimize parameters with a gradient descent algorithm, but your colleague achieved an even smaller error by choosing parameters with their gut feeling. What happened? So any kind of optimization algorithm can fail. Either it cannot converge, or it can converge on a local minimum. In most machine learning, it would be very difficult to beat an optimization algorithm with gut feeling. But in some contexts, if your model represents a physical reality, and if you were trying to do simulation instead of a sort of machine learning approach, and you were defining the model yourself, you, as a domain expert, maybe you might know that you might expect one number to correspond to a pressure and another number to correspond to a temperature or something. And you might have a feeling for what those numbers should be, and it might turn out that you can use that domain knowledge to help you choose parameters. That's not really a machine learning approach. Machine learning is you let the machine learn the parameters. Could a human with domain knowledge, with a good understanding of the underlying model, beat it? Possibly, but it's not really. But the iterative approaches, the machine learning approaches should give you should be able to minimize your cost function and get to the bottom and get the optimal values. Hopefully that addresses your question. How am I doing for time? Right, let's move. I've only got a few slides left. So a few things to keep in mind as when we talk about different algorithms and things. So far we've used, for linear regression, we just took the raw values of the features, which is fine. But when you start to have more than one feature, say for example, we were looking at number of bedrooms and the age of the house and the size, in order to try to predict the house price better. One of the things that you might need to take into account is the fact that the scale of this number might be different from the scale of this number, and it might be different from the scale of this number, which would mean that one of these features would dominate over the others. When you were trying to work out the effect of these features on the total, the direction that you would have to move in with these algorithms and things like that, one dimension would dominate over the others. So often what we'll do, and I'll come back to this, is that you have to scale these for many algorithms before you apply the machine learning algorithm, so that the feature, all features are considered equally. It's a very quick one for linear regression. This is, I mentioned the normal equation. That is how you calculate your parameters theta exactly for linear regression. I think that is actually included as an example in, possibly included as an example in the linear regression practical that you might look at. But in some ways, this is less important because this is only possible in the very simple example of linear regression. Normally, we can't work out analytically the precise values that optimize the cost function. This final example, as we are, I think we're over time, so we'll just pick out a couple of points here. Often your hypothesis function will be a function of many variables. We often label this as theta 0 so that the 1s and the 2s and the 3s match up. So we often count starting from 0 from our parameters for this reason. And it means that going from something like this, we can represent this as vectors and matrices. And this will start to become obvious. But if I want to write, another way of writing this expression is as a vector multiplication. So I take this this vector, put it on its side by taking the transpose, and then it's like doing the normal dot product here. It's just a vector times a vector. So a normal dot product is theta 0 times 1 plus theta 1 times x1 plus theta 2 times x2 plus theta 3 times x3. If we define x0 as 1, we can just write this as all as the x's and all as the thetas, and then we can write this as the matrix equation like this. So I'm showing you this now. It probably doesn't really matter for this course, but normally once you all of these equations for finding parameters given multiple points, it all ends up as linear algebra, as a matrix multiplication. as sometimes called tensors. So one of the frameworks for machine learning, you might have heard of TensorFlow. Basically, it's just representing everything, these kind of equations with parameters and x values as matrix multiplication. And that's the kind of calculation that's going on under the hood an awful lot of times, as you'll see. We mentioned linear regression. There are, of course, other models. It doesn't have to be values of x. You can do x squared and x cubed and so on. In this case, feature scaling becomes even more important. The key point is that whatever form you choose for your model, you can still do use the same optimization algorithm to find your thetas. You can still do a gradient descent type algorithm for an arbitrary cost function, a bumpy surface in many dimensions, but you can still find the minimum by moving down the slope. And that is it's actually what happens in neural networks, again, as we'll come on to tomorrow. So I think we're already running a little bit. Oh no, I said 11:35 lunch. We're spot on. Good. 12:35 lunch. Okay, so does anyone have any last questions about linear regression before we break for lunch? Yes, Yin?
Early on, you mentioned the use of a random number. Is it not used in linear regression, or is it used sometimes and not other times?
Yeah. So in the standard gradient descent here, we weren't using a random number. We were just taking each point in turn and going down the slope. The random numbers often come when you use an optimization algorithm, for example, like stochastic gradient descent, which is very similar, but instead of using it every row of your data at every pass of the algorithm, you pick just one data point at random, one row in your table, and then move. See, yeah, I'm trying to describe what's actually happening in terms of the slope. I don't think I'll go there, but the simple gradient descent algorithm is not random. It is entirely it will always give the same values. In practice, particularly once you get onto the algorithms that are often used with neural networks and so on, there is some randomness involved. So yes, you're right. In what we saw for linear regression here, with this simple standard gradient descent algorithm, there is no randomness. The randomness normally comes from the optimization algorithm. And in this case, we chose a simple optimization algorithm with no randomness. But with neural networks, that is often where the randomness is introduced. Okay, let's wrap up for just now. I will be back at 1:30, and we will start the linear regression practical then. I'll probably try to turn it up, depending on how I'm doing for time, 5 or 10 minutes early to give you a hand if anyone's still having trouble with connections. Otherwise, we can keep on doing that as we get to the first practical. Paste the link to the slides again, please. Certainly. Actually, you don't need the tree main there, but yeah, it'll work. Okay, thank you all. I will restart at 1:30.